Welcome to section 2-8. We are talking about inverses today, and believe it or not, you are well acquainted with inverses. Let me show you how. I have an equation, x plus 3 equals 5, and I want you to solve this for me. And so what you would do is say, well, I want to get x by itself, so I'm going to subtract 3 from both sides. Well, my question is, why do you subtract 3? The reason is because subtracting 3 is an inverse operation of adding 3. And when you put them together, they cancel each other out. And so that is how you move something from one side of the equation to another. And that is an example of using inverses in math. And we do that all the time with multiplication and division. And it turns out that you also are going to use inverses when you're looking at functions. We will talk about why and how a little bit later, but first let's talk about what inverses look like and how they behave. So we have an equation that we've looked at before, the square root of x minus 3. That means that it's a root function and it's moved 3 places to the right. Oops. And it looks something like this. Graphically, what an inverse is it's a graph that is flipped over the line y equals x. So what that means is, it's not a very straight line, sorry. Let's fix that. There we go, there's the line y equals x. And so if you would take your paper and you would fold it on the orange line, and if you imagine that the white graph has wet ink, where it would duplicate when you fold over the orange line is right here. And this would be the inverse of that root. So graphically, that is what we mean by the inverse of a function. Okay? Algebraically, we have a way of calculating what the function is when we want the inverse. So let's take a simple example. F of x equals 3x plus 2. That's a line. And if I want to calculate the inverse, so find the inverse, a lot of times graphing is not very accurate because we're kind of sketching along the way, and we actually want an equation so we can calculate exact values. So how do you find the inverse algebraically? The first step is that you switch your x and y values, and then the second step is that you solve it for y. And the challenge can come in with that whole solve for y. Like sometimes that's easy and sometimes that's hard. So we'll do a couple examples and show you how to do that algebraically, and then we'll talk about the purpose. So if I want to find the inverse of this line, I am going to first switch my x and y positions. So I'm just flip-flopping this x and y value, and then I'm going to solve it for y. So I'm subtracting 2, and then I'm going to divide everything by 3. So I get 1/3 x minus 2/3. And this is my inverse. Now the notation for an inverse is f to the minus 1 of x. That minus 1 is like a in the power position. It's not a power, but that's the notation for an inverse function. So I would say the inverse of f of x is 1/3 x minus 2/3. Okay. Now, just for fun, we won't do this with every problem, but just so we can look at it graphically again, if you draw these, let's draw the first one first. I'm going to do the original function in orange. So we've got a y-intercept of 2, and we've got a slope of 3. So up 3 over 1. Okay. So here's what this line looks like. Like that. And then I'm going to graph this inverse on the same axis, and I'm going to, so it's got a y-intercept of negative 2/3, so I kind of have to estimate that. It's about here. And then I'm going to go from there, I'm going to go up 1 and right 3. So it looks roughly like this. Okay, and you can see that these guys are symmetric across this line y equals x. So our graphical interpretation is holding up in this sense. The orange line flips onto the pink line when you fold on the blue line. All right, let's do some more examples of a more complicated example of finding an inverse algebraically. Okay, this is the one that we did above. Let's find the equation of the inverse. Actually, I'm going to call this f of x. Okay. Okay, so first step is to switch your x and y. Okay, and then we are going to square both sides. And then we're going to add the 3 over. Okay, now I want to show you an interesting dynamic. First of all, let's talk about the domain. Well, let me draw it first. This happens with not every function, but it does happen with roots and their inverses. So here's the square root. We drew this earlier. Okay, and now I'm going to graph this. I'm not going to flip it. I'm just going to actually graph it. This is a parabola, and it's shifted up 3. So it looks like this. Okay, now if you'll notice, these don't look similar. The parabola is in the correct position on this side. That's what we drew in the first problem, but I've got another side to the parabola that I don't have down here on the square root. So what's the deal? The deal is the domain. So the domain on this function we've talked about is a root, and it's restricted. So that means that I take the inside of the root, so we're looking at domain right here, and I make it greater than or equal to 0 because it's a root. That's my rule. So that means x is greater than or equal to 3. That's my domain. The range, okay, where does this, we're looking at this graph right here, where does this graph go y value wise? Well, the y values run from 0 on up, so y is greater than or equal to 0. What happens with the inverse, because we switch the x and the y value, remember that's your first step, is you switch the x and a y. Well, that means that when you come and you figure out the final function for your inverse right here, your domain and range also switch. So now this is my inverse. So because the original function had a domain of x is greater than 3, now the inverse has a range of y is greater than or equal to 3. So basically the x and the y's switch positions, and it's got a domain of x is greater than or equal to 0. So the interesting thing is this parabola is not entirely accurate. Because the domain is x is greater than or equal to 0, it's actually only this piece of it and not this side of it. So we would put our answer right here. What we would say the inverse is, we'd say the inverse function is going to be x squared plus 3, but we put a domain restriction. We'd say the domain is only for x is greater than or equal to 0, which means don't draw that left-hand side of the parabola. And the reason is because the original function had a restricted domain. Now, that didn't happen in this problem because our original function here didn't have a restricted domain. So everything goes and the inverse works out quite nicely. Okay, but so that's something to consider as you're solving these problems. Okay, now let's look at a problem that is challenging algebraically. That last one was a little bit tricky graphically, but let's look at one of the more challenging problems algebraically. Okay, here's this function, and the directions say find the inverse. All right, game plan's the same. We're going to switch the x and the y. So this becomes the x, and both of these x's become y's. Okay. And maybe the first thing to do is to clear out fractions. We don't typically like fractions. So if I multiply on both sides by the denominator, I can cancel that out. And I'm going to distribute in this x. So I get xy minus 5x equals y plus 3. Now, this is something that is going to carry over into calculus, this principle. If you have an equation and you are trying to solve for something, so we're trying to solve for y, and you have two of them, okay? So I'm going to write this. If you have two of what you're solving for, the strategy is this, and this strategy will carry over into multiple different sections. So this idea is something you want to put on a note card and you want to memorize it. If there's two of what you're solving for, the first thing that you're going to do is get all of the terms on one side that contain what you're solving for. All right. Now you can write that in your own words if something else makes sense. But the idea is, in context of our problem, is I've got two terms that have a y in it. So I want those two things on one side and everything else on the other. So in my example, what I'm going to do is I'm going to subtract the y over. Okay, so I'm going to get xy minus y. And I'm going to add the 5x over to get that on the other side. So basically you're isolating all your terms that have the thing that you need, okay? The second step is that you're going to factor out what you're solving for. And that's the trick. And that's going to be consistent in any kind of algebra situation like this. Factor out a y, and I'm left with an x minus 1 here. And what that does is it takes what was previously two unknowns and makes it into just one unknown. And your last step then is divide to isolate what you're trying to get by itself. So we get y equals 5 plus 5x over x minus 1. Okay? And that is going to be your inverse. So the algebra on these is tricky. There will definitely be one of these on your test. Make sure that you work several of these and you understand the algebra on this. It's a super important problem, okay? You could even pause this video and work this one again and try to do it without looking. That would be a great idea. All right, now let's look at one other example and consider a problem that can occur. Let's look at this function. So I want to find the inverse, so I'm going to switch my x and y. And then I'm going to solve for y. So I'm going to subtract the 5. And then I'm going to square root both sides. Now when I square root both sides, I get a plus or minus. Always remember that plus or minus. Okay, let's graph these and take a look at what's going on here. So the original function, I'll do this in orange. This is a parabola and it's shifted up 5. So it looks like this. Okay. And my inverse is right here. And it's a root and it's shifted right 5. Now, what does this plus or minus do? Well, it's two different graphs. The positive means keep it the same. The negative out in front, you remember what that does to the graph? It flips it down. So there's an additional part to this, which is the bottom part of your parabola. Now that looks about right, right? That is symmetric about the line y equals x. They look flipped, they look the same. What's the big problem? Anybody know? If I run a vertical line through that inverse, this is not a function. And that's a really big problem because, again, in calculus, all we want to look at is functions. Okay, so how do we know? So not every listen, this is a statement. Every function has an inverse, but not every inverse is a function. Okay, so if I start with a function, I can flip it, but that may or may not be a function. So the question is, how do I know if my inverse is a function? Well, the way I figure out if something's a function is if I run a vertical line through it and it touches 2 points at one time. Well, what's the flip of a vertical line? If I take this green line right here and I flip it across the blue, that becomes a horizontal line on the original function. So the idea is if the original function doesn't pass a horizontal line test, then the inverse will not pass a vertical line test. Okay? And so the answer is that the original function passes a horizontal line test, not a vertical, because we're flipping it back to the original function. Okay? And if that happens, if a function, whoops, passes the horizontal line test, we say it is 1-to-1. And the shorthand for that is 1-1. So that's a vocab word that'll show up in your directions. So for example, in your homework, I might say, is f of x equals 1/x 1-to-1. Now this is where your knowledge of graphs is really going to help you. I know what this looks like. I know that it's a swoosh up top and a swoosh down below. So will it pass a horizontal line test? The answer is yes. I don't even have to draw it. I will draw it for you just so we're all clear. But if you can do these in your head, if you can picture them. So here's this and here's this. That's the parent graph, 1/x. Does this pass a horizontal line test? I run a horizontal line through all these values. Yeah, I only ever touch the graph one point at a time. So the answer is yes. As opposed to y equals x squared plus 3x plus 1, what is this picture of? Well, highest power is a 2, so it's a parabola. Doesn't really matter where it is. You could draw it anywhere. It doesn't matter. It's not going to pass a horizontal line test, so this is not 1-to-1. Okay? Now, that's how you conceptualize an inverse graphically, and how you find it algebraically, and how you know it's a function. So why do we care, and what does it do? To answer that question, let's take a look at 2 we calculated earlier. Here's a function and its inverse, and let's see how they interact. The interesting interaction is when you do composition with the 2. So if you take a function and you compose it with its inverse, okay, remember, and I can write that way, or I can write it this way. This means put the inverse into the original function. So let's go ahead and do that and see what happens. I'm going to take this inverse and I'm going to plug it right in here, okay? And so what I get is the square root of x squared plus 3, and then I've got a minus 3 there. Well, when I simplify this up here, the 3's cancel, and then when the 3's cancel, that root and the squared cancels, and I get x. Okay, now hang on. Let's look at the other direction as well. What if, because we remember we said that function composition's not commutative. Order matters. So let's say, what if we take the inverse first and plug the original function into that? So now we're taking this function and we're going to plug it into there. Okay, that means I'm going to go root x minus 3. That thing is squared, and then I'm going to add 3. The square root and the squared cancel, and I'm left with this. The 3's cancel, and I'm left with this. Is that a coincidence? It is not. Okay. If two functions are inverses of each other, then let's call these two functions f of x and g of x, just for fun. Okay, so we've got two random functions, f and g. I want to know if they are inverses of each other. Then, if I take one and compose it with the other, I will get x. And if I do it the other direction, I will also get x. So the fact that I'm getting x with both of these means that these are indeed inverses. Now, we knew that originally because we calculated them to be so, but that is what they do. So here's what's interesting about it. Remember our original problem? I said, hey, let's look at this, and you do the inverse function to solve it. These cancel and they give you 0, right? That's what we've understood with addition and subtraction. They cancel and they give you 0. Now let's look at division and multiplication. In this situation, when I do the inverse operation, they cancel, but they don't give me 0. They give me 1, right? I mean, we don't usually write the 1, but that's what's happening. 3 divided by 3 is 1. So inverses behave differently depending on what the operation is and what kind of system you're looking at. So with addition subtraction, your inverses give you 0. With division multiplication, your inverses give you 1. With functions, the inverses give you x, and they give you x through composition. So I think that's kind of cool. That just it's a different, they're behaving similarly, but your outcome's different because we're looking at functions. So if you want to confirm that two things are inverses, you can do it that way. You can find them algebraically, and you can find them graphically. Try some problems, and I'll see you next time.